Hello, my name is Gayane Vardoyan, and today I will present our work titled On the Exact Analysis of an Idealized Quantum Switch, done in collaboration with Saikat, Guha, Philippe, Nain, and Towsley. In this talk, we will focus on a single quantum switch, which is a simple example of a distributed quantum system. Distributed quantum systems have many uses, and these can be broadly divided into three categories: cryptography, which includes quantum key distribution; scientific applications, including high-precision clock synchronization and baseline imaging; and distributed quantum computation. In general, quantum communication offers functionality that's not achievable classically, and this is often achieved by exploiting the properties of entangled quantum states. The rest of the talk is organized as follows. I will give you a brief introduction to quantum computation and communication. Next, I'll introduce the problem, which involves a quantum device called a quantum switch. In this section, I'll describe the operation of the device and discuss the problem formulation, analysis, and results. Finally, I'll conclude with a summary and future directions. We start with the introduction. A qubit is the quantum analog of a bit and can be represented by a two-level quantum mechanical system, such as photon polarization or electron spin. These states can be represented using Dirac notation, as shown here. For example, an electron with spin up can be mapped to state 0 and with spin down to state 1. Unlike a bit, a qubit can be in a superposition of states, as shown. Here, alpha and beta have a probabilistic interpretation, and their magnitude squared must sum to 1. Two or more qubits are said to be entangled when the state of one cannot be described independently from the state of the others. One type of entangled state is known as a Bell state or Bell pair and is the single most important resource for quantum communication. This is a two-qubit state where the two qubits A and B may be separated by an arbitrary distance. Even in this case, if we measure qubit A and get 0 as a result, then we know with certainty that qubit B is also in state 0. And similarly, if we measure one of the qubits to be in state 1. Let us now look at an example of a quantum distributed task. We will look at one iteration of the E91 protocol, which is an entanglement-based quantum key distribution protocol. The goal for the users is to create a one-time pad, which is the only provably secure means of encryption. To do this, they use a quantum network to generate a Bell pair. One qubit is given to Alice and the other to Bob. Next, the users randomly choose one of a set of different measurements to perform on their qubits. If, for instance, they both choose the computational basis for their measurements, then they will both obtain the result 0 with probability a half, or the result 1 with probability a half, hence generating a raw secret qubit. But had they chosen different bases to measure in, their results would be uncorrelated. Alice and Bob repeat the process until they have generated enough raw secret qubits to be distilled into a usable one-time pad. A unique feature of these types of protocols is that even in the presence of an all-powerful adversary, Alice and Bob can use sensitive statistical methods to detect eavesdropping. There are many such promising and exciting distributed quantum system applications, but they do come with their own challenges. One of the most significant challenges in quantum communication is transporting a quantum state over a long distance. A qubit can either get lost or altered in an undesirable way while in transit. In general, for a fiber optical link, the probability that the photon reaches the receiver depends on the link's transmissivity, which is given by e to the minus alpha L, where alpha is the fiber's attenuation coefficient and L is its length. Clearly, a longer channel means higher loss probability. One method of dealing with losses in a classical network is to use repeaters, which take as an input weak, distorted, or noisy signals and generate clean and strong signals. On a quantum channel, such an operation is prohibited. That is, we may not take an arbitrary or a non-quantum state and create an independent copy of it. This is a result in quantum mechanics known as a no-cloning theorem. So how can we help Alice and Bob transport quantum states to each other? We can create a simple quantum network by positioning a device between them known as a quantum repeater. The users will generate entanglement between themselves and the device. These link-level entangled states are Bell pairs that we saw in previous slides. The repeater will then perform a local operations and a measurement collectively known as a swapping operation, the result of which is a longer distance Bell pair, directly entangling the user's qubits. This new Bell pair can now be used as a resource, for example, to teleport a quantum state or to generate a raw secret qubit in entanglement-based quantum key distribution. Note that due to non-idealities within the quantum repeater, the swapping operation may fail. Also, to generate the elementary link-level Bell pairs, we must still send photons between the users and the repeater, which means that the probability of successfully generating these states will still depend on the link's transmissivities. In this work, we will discuss how these phenomena may be modeled. We can extend the distance between two or more users by, for example, chaining quantum repeaters as shown in this example. Here, all links first attempt entanglement generation at the link level, and each repeater performs a Bell state measurement. The final result is an end-to-end entanglement shared by the users. In future quantum networks, each of these devices may be connected to many other devices and users, so it's reasonable to assume that these devices will be equipped with entanglement switching logic. Hence, from now on, we use the term quantum switch instead of repeater. To gain insight on how such networks will operate, our goal is to model and analyze a single quantum switch. Specifically, very interested in obtaining its capacity and getting an idea of how many qubits is an appropriate amount for this kind of device. So that was our problem statement. And now we move on to the switch description. I'll describe the switch in quite a bit more detail and cover some key components of its architecture and operation. First, since we are interested in the performance of the switch, it's reasonable to assume that the endpoints are quantum-equipped users with infinite and noiseless quantum memories. This will ensure that the endpoints do not limit the performance of the switch. Next, the switch is also equipped with some quantum memories. In this work, we will focus on a simple problem formulation wherein the memories at the switch are also infinite and noiseless. In the graphic, gray circles are for unoccupied and red are for occupied quantum memories. Finally, the switch can perform projective measurements and will be capable of classical communication. The switch will serve k users, and its operation consists of two steps. The first step is Bell pair generation over the individual links, and the second step is end-to-end quantum state generation via swapping operations. We will model link-level entanglement generation as a Bernoulli process with parameter p representing the probability of successful entanglement generation at the link level. We assume that all links are identical so that they all generate Bell pairs with the same success probability, which is approximately e to the minus alpha L, with alpha the fiber attenuation coefficient and L the link length. The second step involves entanglement swapping based on user demands, or switching policy. Let's examine that in more detail. At any time, the switch has three options: perform a swapping operation, store the qubit in memory, or wait. Suppose at the beginning of a time slot, all links successfully generate Bell pairs. Suppose that the two users on the left wish to share an entangled state. The switch performs a Bell state measurement, entangling the two users' qubits. Still within the same time slot, the switch may continue to perform entangling measurements as long as there are users who wish to share entanglement and as long as those users share entanglement with the switch. In the next time slot, suppose only one link was able to successfully generate a Bell pair. In this case, the two qubits are stored until another link also successfully generates a Bell pair. In time slot 3, suppose that another link was able to do so, and if the two users wish to share entanglement, the switch may now perform the entangling measurement. It's worth noting that successfully generated quantum states are sometimes not what they ought to be. Fidelity is a measure of closeness of a quantum state to the desired quantum state. In this work, we assume that all quantum states have unit fidelity to the corresponding ideal pure states. Let's briefly discuss prior work on this problem. In prior work, we modeled link-level entanglement generation as a Poisson process and modeled the quantum switch using a continuous time Markov chain. We found that this model was easily extendable to explore a switch with a finite number of quantum memories, or a switch that services users with non-identical links, as well as systems where quantum state decoherence is non-negligible. In another generalization of this model, we explored multipartite entanglement switching, but only for an idealized quantum switch. One of the goals of our present work is to compare continuous time Markov chain and discrete time Markov chain analyses and note any discrepancies in the resulting performance metrics. We are now ready to discuss the analysis of our idealized quantum switch. If the system we have just described is in steady state, then we define its capacity C to be the number of end-to-end entangled states generated per time slot of length tau seconds. We denote the number of stored qubits at the switch with E of Q. Since we are interested in the capacity of the switch, which is the maximum rate of entanglement switching, we must assume that any pair of users wish to share an entangled state, as an arbitrary switching policy would likely fall below the capacity of the system. For the same reason, we will assume that bell pairs will be used in entangling measurements as soon as there are enough of them to generate an end-to-end bell pair between two users. We also assume the switch follows the oldest link entanglement first rule, wherein the oldest link level bell pairs have priority for being used in entangling measurements. Note that this policy doesn't affect the capacity, but it does happen to minimize the number of stored qubits in steady state. Let us summarize our modeling assumptions. We model link-level entanglement generation as a Bernoulli process, where P is the entanglement generation success probability. Quantum memory coherence times are assumed to be infinite. However, entanglement swapping only succeeds with probability Q. We use discrete time Markov chain to model the system. It has a state space given by the set omega, which is the set of non-negative integers. This is sufficient because of our switching policy, which ensures that only one link will have stored bell pairs at any given time. Here's a graphic of a small portion of the discrete time Markov chain. State I represents the case where one link has I successfully generated stored bell pairs. The system has a probability of remaining in this state if, for example, no links were successfully able to generate bell pairs in a given time slot, but note that there are other events that can cause this self-transition. The chain moves forward with probability Pf. This transition occurs when all links except the one that already has stored bell pairs have failed to generate bell pairs. Backward transitions occur when stored bell pairs are used in entangling measurements. Next, we look at the analytical and numerical results. We prove that the system is stable if and only if the number of users k is strictly greater than 2. We also derive a closed-form expression for the capacity, which is given by the number of users, multiplied by the link-level entanglement generation success probability, divided by 2 since this is the number of link-level bell pairs needed for one end-to-end bell pair, and all of this multiplied by the swapping success probability q. These results match the continuous time Markov chain analysis results exactly. For the expected number of stored qubits, we can take a look at the expressions obtained from the analysis of the continuous time and discrete time Markov chains. Note that for the continuous time Markov chain expression, there is no dependence on the entanglement generation rate. But for the discrete time Markov chain expression, we have to solve a polynomial of degree k for beta, which does have a dependence on the probability of successful entanglement generation at the link level. Let's look at some numerical comparisons of the expected number of stored qubits in steady state. In these plots, the blue curve represents the discrete time Markov chain result, and the red represents the output of the continuous time Markov chain analysis. We measure the discrepancy between the two curves using the maximum relative error taken over all possible entanglement generation success probabilities p for a switch servicing a given number of users k. We observe that the discrepancy diminishes as the number of users grows, and even in the worst case, which occurs in the area indicated, the difference between the two results is less than a qubit. I conclude the talk with a summary and future directions. In this talk, we introduced the bipartite entanglement switching problem and modeled it as a discrete time Markov chain. We analyzed the stability of the system and derived expressions for the capacity of the switch, as well as the expected number of stored qubits in steady state. We found that for the highly idealized problem that we studied here, there isn't much of a difference between the continuous and discrete time Markov chain models. The problem formulation studied in this work extends beyond entanglement switching and can be applied to any kind of bipartite kitting process or stochastic assembly like Q. As I mentioned, and as the title of our paper suggests, we studied a highly idealized distributed quantum system in this work. There are many possible extensions of it, such as link heterogeneity or working with non-unit quantum state fidelities or constraining the switch to have a finite number of quantum memories and imperfect qubit storage as well as other state decoherence. And some of these extensions have already been studied using continuous time Markov chains. Unfortunately, extending the discrete time Markov chain to include these features is highly cumbersome, as it increases both the number of transitions between states as well as complicating the transition probabilities themselves. So more work is needed in order to fully characterize the accuracy of the continuous time models. This concludes our talk. Thank you for listening, and if you have any questions or comments, please do not hesitate to contact any of the authors.